Hello students, it's your professor Dr. Mink. Welcome to another exciting lecture. Well, they're exciting to me. An exciting lecture for CSC 223, Comp Sci 2, Data Structures and Algorithms, and the topic at hand at the moment is queues, which is covered in chapter 14 of your textbook, Java Foundations. If you tell me that you've never experienced a queue before, I bet I can prove you wrong. Let's get started. Here are the topics that make up the scope of this lecture. We'll discuss queue processing, using queues to solve problems, various queue implementations, and comparing queue implementations. Because remember, a queue, well, not remember, as you might have guessed, a queue is an abstraction. And how it's implemented is abstract to the user. The protocol that the queue follows is all we really need to be concerned with. In our lengthy discussions about stacks, you heard me no less than 500 times. Now that's an exaggeration, but many times mention the protocol of a stack, which is LIFO. A stack is a storage or a collection structure, and it stores elements in a linear fashion, and they are accessed last in, first out. A queue is a collection where elements are added on one end and removed from the other end. Therefore, the protocol, the management protocol for a queue is FIFO, first in, first out. Elements are removed in the same order that they are placed onto the queue. So here's where I may prove some of you wrong if you said I've never used a queue before. The checkout line at a grocery store is a queue. Cars at a stoplight are a queue. An assembly line is a queue. So yes, we've experienced queue structures in life every day. Here we have a graphic depiction of a queue. It's a conceptual diagram, but we have a couple of key components. You've got the rear of the queue, where elements are added, the front of the queue, where elements are removed. And in this diagram, the artist attempts to depict adding an element and removing an element, adding an element to the rear of the queue, removing an element from the front of the queue. If you recall, the operations for a stack were push, pop, size. We had peek. The standard queue operations are NQ, which adds an element to the rear of the queue. DQ removes an element from the front of the queue. First examines the element at the front of the queue. Is empty, determines if the queue is empty. Size determines the number of elements on the queue, and toString returns a string representation of the queue. So NQ is comparable to push. DQ is comparable to pop. First comparable to peek for the stack, obviously. The Java Collections API isn't consistent about implementing collections. For queues, the API provides an interface, the Q interface. Then various classes, for example, linked list, are used to implement the interface. The Q interface defines two versions of the methods that add and remove elements from the queue. The difference in those versions is how specific situations are handled, which we will drill down on in this lecture. There's a method named add, and it throws an exception if the element cannot be added. And there's also a method named offer that returns a Boolean indicating success or a failure when trying to add an element to a queue. When the queue is empty, the remove method will throw an exception, and the poll method returns null. And obviously, we are going to see very detailed demonstrations of all of these methods, so don't worry about understanding these at this point in time. We're just talking at a conceptual level. So the goal of the API is to help the user handling exceptional cases, whichever way is preferred. And you'll see the different options as we get into the interface and the actual implementation. If you took the prerequisite course, CSC 122, Comp Sci 1, Object-Oriented Programming with me, you probably remember the Cesar cipher program. Cesar cipher encodes a message by shifting each letter in a message by a constant amount k, and it shifts its numerical value. It adds k to its numerical value using the Unicode numbering system. So we're going to use a queue to help us encode and decode messages. So if k is a 5, A becomes F, B becomes G, etc. And it's fairly easy encoding to break. It's not something we would use to send a message to a nuclear submarine to attack another country. No, we use a much more complex encryption encoding system. So an improvement can be made by changing how much a letter is shifted depending on whether the letter is in the message or not. And we're going to play around with this, and we'll have some fun with this example. I think I will. Hopefully you will too. So let's introduce a new term with regards to encryption. A repeating key is a series of integers that determine how much each character is shifted. So for example, here's a repeating key, 317425. So, and you've got a message that contains, I don't know how many characters, 723,287, right? So the first character in the message is shifted by 3, the next 1, the next 7, and so on. And when we get to the 7th character, because the key is 6 long, it's shifted by 3, and then the 8th by 1, then the 9th by 7. It just continues to repeat itself, which makes the encryption a little more complex in shifting every character by K. Here we have a graphic depiction of a message being decoded using a repeating key. And we're using that same repeating key, 317425. So there's the encoded message, and basically take it letter by letter. N minus 3 equals K. Think about it, K, L, M, N. K plus 3 is N. O minus 1 is N. V minus 7 is O. A minus 4 is W. And you get it, etc., etc., etc. On and on and on. Now let's take a look at a program that uses a queue. And this is pretty straightforward, simple program. Public class codes, has a main in it. So first we use an integer array, an array of ints, to store the key. And we have a 7 integer key that'll be used to encode and then decode. So, and here's the message. We're not even soliciting it from the keyboard. All programmers are playwrights and all computers are lousy actors. Here, instantiating a new queue of integers named encoding queue. Remember, queue is an interface implemented by linked list. So queue, integer, decoding queue, new linked list. So we have a queue for encoding the message and a queue for decoding the message. So then we got a for loop. Int scan 0 less than key.length, less than the length of the array. And we're adding key subscan to this queue. So the queue will hold the key. Remember, it's first in, first out for a queue. Then this for loop, key value, encoding queue remove, dot remove. Remove will remove the first one in. Encoded, which is that string, plus equals char message.char scan plus the key value. So we're going to take the character at 0 and we're going to add the first key value to it. Then we're going to take key value and add it to the encoding queue. It'll get added at the end. And notice I have a breakpoint on this one here. And then we're going to print the encoded message. And then we'll do the reverse for decoding. So let me run this with this breakpoint and you'll actually see the queue. So here we have, let me see if I can, that's not going to work. So here we have the message stored in a string. Coding queue, decoding queue. And we have, let me see, the key value, the 5. And here's the decoding queue because we haven't changed that yet. We just loaded it with all the values. 5, 12, -3, 8, -9, 4, 10. That's our key. Encoding key, I should say. I'm not an encoding expert, so I'm probably butchering the terminology there as far as encoding, decoding. But we're most interested in queues right now. So we removed the first item in the queue, moved it to key value, and then encoded, which was an empty string, plus equals character message.char scan plus the key value. So we're going to take the char 0 and we're going to add the integer key value to it, and we're going to then add that to encoded, which starts as an empty string. And then we're going to add the key value to the end of the encoding queue. So here at this point in time, look at the difference between the encoding queue and the decoding queue. The 5 is missing from the encoding queue. Why? Because it's currently stored in key value. We're about to add, and we're using that, so it's off the queue. We're using that to encode, and then we're going to push it, equivalent of pushing on a stack, pushing it back onto the queue. There we go. So now, there's that 5, which was at the beginning, and it's now last. So we're just going to recycle this queue over and over again, and we will then encode the message. So encoded now holds an F. A plus 5 is F. If you move 5 characters to the right from A, you get an F. So that's part of the encoded message. And there you go. And then L plus whatever the key is right now, L plus 12 gets us to X. And so we keep on going, and you will see each letter get encoded. Now, I'm going to just run this for you, and you'll see. Here's the encoded message, FXI, and here's the decoded message. That's how a queue works. Of course, I'm going to put this file in the Canvas timeline, and by now you should know what to do with it. You're not going to understand a queue by just watching this video and putting a checklist or check in the box understanding queues. It's not going to happen. Download this, play around with it, and I'll probably, I'm still thinking about what assignment, what programming project I'm going to give you this semester for queues, but it'll be a challenge.
Here we have a diagram showing the relationship between codes program, linked list, and the interface that is used, the queue interface that is used to implement the linked list. Next up, we have another fun example. Well, fun for me and hopefully fun for you. We're going to use a queue that will simulate the waiting line at a movie theater. And we need to determine how many cashiers are needed to keep the wait time below 7 minutes. So here's some assumptions for this scenario. Customers arrive every 15 seconds, and processing a request takes 2 minutes once a customer reaches a cashier. So remember, given those parameters, we want to keep the wait time below 7 minutes. Still pretty long for me. I'm an impatient person, but oh well, let's get started. So here we have the ticket counter program, and it starts with this customer class, and each customer object has an arrival time, integer that's an arrival time and a departure time, a couple methods. New customer can be created passing an integer as the sole parameter, and that integer is the arrival time, or sets the arrival time. The departure time is always 0. That'll get set later. And we also have get arrival time, returns an int, returns the arrival time, set departure time with an integer parameter, get departure time, and total time returns an integer, which is the difference between departure time and arrival time. So Here we have the ticket counter program, which utilizes a queue. Remember, queue is an interface implemented by the linked list class. So we create a new object reference variable customer, named customer, and we create a new queue of customers, and its name is customer queue. It's a linked list. And then we have an integer array cashier time set at the maximum number of cashiers. Now, I've changed these numbers here because I was running this thing preparing for this video, and the numbers were set at, I want to say, 10 cashiers and 100 customers. And these for loops which load the queue with customers just run and run and run and run, and I've got a couple breakpoints. So if you swipe this off the Canvas timeline, it'll probably have those numbers there. And just for testing purposes, you may want to change those to more manageable numbers. So we've got our outer for loop. So from cashiers equals 0 to cashiers less than max cashiers, which I have that set at 5. We start by setting each cashier's time to 0 with a for loop. And then we load the customer queue. And we go from 1 to number of customers, and we add them to the queue, and their arrival time, remember, if you think back to this previous slide, they arrive 15 seconds apart. So the first one, which is going to be count sub 0, we're going to shift that with a 1 when we print them out. But 0 times 15 will be 0, and then 1, 15, 30, 45, 60, 75, etc. Total time 0. So while the customer queue is not empty, we're going to process all the customers in the queue. And we're going to add each of their time. And then we simply, we get an average time, and then number of cashiers plus 1. There's the shift, and the average time plus the average time. So, and we'll do this for multiple numbers of cashiers. So I've got a couple breakpoints here just so you can see how this works. Let's step into this this program. Let me close the last run I had. So, okay, so here we are. If I look at my variables, we've got our customer queue. Customer queue has already been loaded with 5 customers. Arrival time 15, 30, 45, 60. And remember, this is FIFO, first in, first out. So the first thing we're going to do is we're going to remove, using FIFO, a customer from the customer queue and assign it to this object reference variable, which points to a customer. And then we'll process start time, etc. So let's step into this. Actually, I'm going to put another breakpoint. I'm going to run right down to the end where we've processed that, because it takes a lot of clicking if you single step into this, which I've done already to make sure everything was honky-dory, technical term. So here we are. Okay. So okay. Total time 120. Cashier time should be 135 for those customers, and we'll walk through this, and we should get some output for the first iteration of this. Oops, sorry. Okay, so for one cashier, 5 customers, the average time is 330 seconds, which is 5 minutes and 30 seconds. Then we're going to increment the outer loop, and we're going to have second cashier. Rather than keep on clicking through this with the breakpoints, you've seen how the queue works. So what I'll do is I'll disable this breakpoint, and we'll just run it to fruition. And there we go. So with one cashier, the average time per customer, and remember I modified this to 5 customers, it's 330 seconds or 5 minutes and 30 seconds. If we add a second cashier with them, the customer still coming in at 15 seconds apart, and the process time taking 2 minutes per transaction, the average time goes down to 192 seconds, which is 3 minutes and 12 seconds. So, I mean, it basically does some queuing, dequeuing, and some basic math. If I change these numbers to, I think it was, I want to say 7 cashiers and 100 customers, but don't quote me on that. And if I run this program, you'll see the numbers there. So if you have 100 customers coming 15 seconds apart, the average wait time is 5,317 seconds, which is I want to say that's like 80 minutes each. And by adding other cashiers, you can get that down to 219 seconds, which is roughly 3.5 minutes. So obviously, I want you to download the files in this project, put them into a package, run them, and dissect and experiment with the queue. Thanks for watching. This slide shows the relationship between the ticket counter program and the linked list of integers, which implements the queue interface and the customer class. When I made a final run of the ticket counter program, I changed the number of cashiers to 7, which didn't get us to the point where we needed to be. The goal was to get an average time of less than 6 minutes, which is 420 seconds. When you get to 6 cashiers, you're under that 7-minute processing time or 7-minute wait time. But once you get to 8 or more cashiers, you're simply waiting the 120 seconds or 2-minute transaction time. And there's really no, I guess the term would be latency in the queue. So adding more than 8 cashiers will not improve the situation at all. What I'm going to do is I'll change those parameters, number of cashiers. I'll set it to 10, and I'll run a video. I'll run it and put a video right after the slide. So here you go. Hi folks, here we are back at the ticket counter program, and I've changed the parameters: max cashier 10, max customers 100, and I'll run this just so that you do see there is a point of diminishing returns. After you get 8 cashiers and 100 people, 100 customers in the queue, they're really just waiting 120 seconds each, and there is no advantage to adding more than 8 cashiers. I hope this was useful, and obviously you need to download these files. You know the routine. Sorry, couldn't help myself. Let's move ahead. So, defining a QADT, abstract data type, using the classic operations looks like this diagram: NQ and T element, DQT, return type first, is empty, size to string. And we'll look at an actual implementation next.
Now we're going to take a look at a linked queue, a queue implemented with links. And let me start off by saying this is an assignment, a programming assignment built into this lecture. I have a driver program that I created, and here's a sample run. And you're going to take the files from the author, which need a little bit of work. You're going to pull this all together to implement this linked queue system that allows you to enter full names, first and last, and store them in a queue. So let's take a look real quick. The linear node class represents a node in a linked list. And when you look at the implementation here, you can see you've got an element. We're using the generic data type T, and then you've got a next linear node. So there's your linkage. You're storing your element, whatever type object you're storing in this linked queue. And then there's your linkage to your next linear node. And the next linear node would have its own element and a linkage to the next linear node. You've got your QADT class, which is your interface for a queue. Here's all the methods in the QADT class. You've got DQ, NQ. Think of DQ as push, NQ as pop. First is similar to what we used peek for with the stack application. Is empty is kind of a service method, because you're going to need to know if it's empty before you can DQ any elements. List is the equivalent of display. Remember, we displayed all of the items on the stack. List will list or display all the items in the queue. And obviously size and toString. And then we implement the interface with the linked queue class, which pulls together all of these, plus has count, head, and tail. Head is the beginning of the queue, the list that encompasses the queue, and tail is the end. And I've created this queue driver program, which simply has a main, presents this menu, and then uses it just builds the user interface for this particular application. So let's walk through this run, which I just finished. And I'm also going to paste this in a slide so that you can take a look at the user interface that you have to simulate. So we've got our menu, NQ, DQ, first, list, and exit. So first I choose to NQ Aaron Nola. I happen to have been watching a Phillies game when I did this. So I'm adding Aaron Nola to the head of the queue. Then I'm adding Bryce Harper to the queue, Scott Kingery to the queue, and then I select 3, which will tell me what is the first element in the queue. Now remember, when we used peak for a stack, and the stack uses LIFO protocol, we were looking at the top element of the stack. That's not true. Remember, a queue uses FIFO, first in, first out. So the first element, which would be the first element out if we choose DQ, which is kind of comparable to pop. So the first element in the queue is Aaron Nola. Then I choose 4, which is list, which is comparable to the display method we had in the driver for the stack. So elements on the queue, Aaron Nola, Bryce Harper, Scott Kingery, and they are in the order they were added. They are in, first out. So then I'm going to DQ. I'm going to remove an element from the queue. Once again, FIFO, first in, first out. So the first element out was the first element in. I choose 2 again, DQ, DQ'd element, Bryce Harper. Then I choose 4 elements on the queue. There's just 1 left, Scott Kingery. At this point in time, the head is pointing to, the head of the queue is pointing to Scott Kingery. Then I DQ. DQ element is Scott Kingery. Then I try to DQ again. The queue is empty. Remember the is empty method. That has to be developed as part of this assignment. And then I quit. So I'm going to give you linear node, linked queue, QADT, and the empty collection exception, but I did some internal validation that would keep this from throwing any exceptions, because I just basically return null and a message saying the queue is empty, which allows the program to continue. So you're going to have to get into each of these files and make the necessary changes so that your program simulates this program. And of course, I'll put a rubric, and if you have any questions, don't hesitate to ask me. And as promised, here is a screen print of the program I just ran, the run of the program I just discussed in the previous video. Take a look at it. Don't hesitate to ask me any questions. Next, we're going to implement a queue using an array. However, I will say that I think it's easier to implement a queue with a linked list, but we'll go through both. If we implement a queue the same way we did a stack, one end would be fixed at index 0. The problem is that unlike a stack, a queue operates at both ends. Okay, so you're not just data objects are not just entering and leaving through the top. It's a different structure. So to be efficient in implementing a queue using an array, we should avoid shifting elements. One way of implementing a queue using an array is to treat the array as circular. You're probably thinking, what does that mean? Well, that's just a perspective on the array. It's still a regular array, but we treat it as if it loops back around on itself. In other words, the last index is thought to precede index 0. And we'll use two integers to keep track of where the front and rear of the queue with regard to the array are at any given time. This diagram will help you to visualize how we're going to implement a queue using a circular array. So we would have to keep track of the front, and in this case the front is index 3 in this given state. That will change. And the rear is index 7. Therefore, the count is going to be the difference between those two. 7 minus 3 will be the count. Now we come to the inevitable but strange situation where some elements of the queue straddle the end and beginning of the array. So in this case, after moving items onto the queue, enqueuing, dequeuing, we have a situation where the front is at index 98 of an array of size 100. So it goes from index 0 to 99. So front is at 98 and the rear is at 2. And in this scenario, the count obviously is 4, and you can see that graphically depicted in this slide. Here we have a series of snapshots, state snapshots of an array-based queue. And we have the array depicted as you would expect an array, a linear array to be depicted. So in the first snapshot, we have A through H have been enqueued. So A, first item was added as you would expect, index 0, B to 1, C to 2, etc., up to H at index 7. So the variable front holds 0, rear holds 8, count holds 8. Okay? 8 minus 0 is going to give us 8. So after we dequeue, first in, first out, remember, we dequeue A, then B, then C, then D. So now the front is 4, and the rear, after which we add new items to get enqueued, is 8. So the count is now 4. So then we enqueue I, J, K, and L. And they go where you would expect. 8, 9, 0, and 1. So now the front is 4, the rear is 2, and the count is 8. So obviously you could see where this is going. You're going to need some logic that if the front, the index representing the front, is greater than the index representing the rear, you've got some math to reconcile that, knowing the size of the array behind the queue. In case you're wondering how we implement the circular reference or circular array, the wraparound, if you will, what happens is both the front and the rear index values get incremented, and when we get to the last index in the array, let's say if it's an array of size, well, in the example I'm about to post, I set the underlying array at a size of 5, just so I could walk through it and you could see us NQ and DQ and not have to deal with the size of 100 or 10 or 20. And so when we get to index 9 and we've filled it, if we dequeue an element, that element is going to be 0. And then the next element to get enqueued after 9 will have to go to 0. Well, this is the line of code right here that implements the wrap back or wrap around, if you will. And we just use the mod function to capture the remainder. So we take the rear plus 1 and then mod q.length. And if that gets us beyond 0, we'll start over. You're going to see that in the demo that I'm about to post. Now we're going to demo a queue implemented with a circular array. It's a very cool implementation if you ask me, but then again, I'm a nerd. So we have the QADT interface, looks very similar, if not the same, as the one we used for a linked list queue. We have circular array queue, the class that implements that interface, and you could see all the members. We have count, front, the queue, which is a generic data type array, and rear. And then we have all the methods implemented, constructors, one with a capacity, initial capacity, one without, dequeue, enqueue, expand capacity. If you remember when we had a stack implemented with an array, we simply doubled the capacity. First is empty, size, etc. So let's take a look at this. And you should know that this is going to be an assignment. There are several components of this circular array queue that are not operational. They're not coded yet. They're just there as placeholders. And guess who's going to complete this? I'll give you one guess. That's correct, you. So I've placed a breakpoint in the driver program that I created, just like the driver program I created for the other queues and stacks that we've been working on. And I'm going to run this in debug mode, and we're going to take a look at the memory, and we're going to see the underlying circular array structure and how it fills and how it wraps around. So, whoops, sorry, wrong program. Let's and there's the menu structure. So let's just put a couple elements. Now this is implemented, it uses the generic data type T, but I'm implementing it as a string. Even though it's a string, I'm going to just enter numeric values just so you can see them sequentially stacked up, but they'll be stored as strings. So 1, and there's the 1. Okay, so now if we look at there's a circular array of strings, and there is let me see if I can move this over. Of course, there we go. So there is the 1 stored in array index 0. Okay, the front is now, the variable integer front is now 0, pointing to the front, and the rear is now 1. So let's go back. I'll proceed past this. Where did I put that breakpoint? Okay, now it's going to ask for the menu. We'll NQ another element, a 2. It'll be stored as an array. I'm sorry, as a string. We can now see, okay, the front is still 0. The rear is now 2. The 1 is stored as a string in index 0, and the 2 is 1, and the rear, where we will NQ the next element, is back here. So let's do a couple things. I'm going to just plow through this and fill this queue. There's a 3. Okay. We'll NQ the 4. And, just take a look back. So now the rear is pointing at index 4 of the array. And we've got 1 at the front, 2, 3, 4, and the rear is now 4. Okay, let's DQ an element. So remember, the front is now 0, and there's our 1. So pay close attention to the front of the queue. Oops. Enter a choice 2. Okay, we've DQ'd element 1. Now let's take a look. Okay, now the front is 1. 0 is now null, it's available. The rear is still 4. Now let's NQ 2 elements and see where they go. Because at the rear, it looks like we only have 1 index location left in the array. And this is the point where we see the circular array implemented. So let's do this. We'll NQ another element onto the queue. Let me see, I was up to 4. So let's add a 5. Let's take a look where we are. So there's the 5, right? So you would think if this were just a linear array that we'd be out of luck here, right? Because the array size -1 is going to get us to this 4. There's an element there, but watch. Remember, index 0 has been DQ'd. Let me just, before we do this, because this is really the important part of this presentation. The front is now 1. Okay, the front is now 1. If we DQ, that 2 comes off. The element at the front. Matter of fact, I'll do that just so you can see how this is moving. Okay, so let's DQ an element, and there's the 2. And we go back and look at the memory. Now look at the front. The front is at index 2. 0 null, 1 null. So the 3 is now at the front, but the rear where's the rear? The rear is now 0. Uh-oh. So what does that mean? Well, let's take a look. Let's now proceed. Let's NQ an element. So we went up to 5. Let's NQ a 6. Take a look at the memory, and there's our 6. Now where's the rear? The rear is now at 1. Now, here comes the problem that you will fix. Pay attention. So we've got index 1 empty. The front has a 3. Remember that. We'll NQ a 7. Take a quick peek at the memory. Okay. I don't see any open locations. Here's the problem. The front and the rear are now pointing at 2. So what, and I have a 3 at the front. So let's try an NQ, and we should get an error if this is set up correctly. We'll put an 8 on here. Uh-oh. There we go. We've lost data. And if we now DQ, which should have gotten us a 3, because that was we're still in a FIFO protocol. So now let's DQ. We no longer have FIFO protocol because this program is incomplete. Okay, it doesn't manage the size. It doesn't. If we go back to expand capacity is not working. Yeah, a lot of this stuff is not working. Now I'm going to stop now, and but your assignment is to make all this work, and I'll have a rubric and detailed instructions, and I'll also have a video showing all of that working. But for now, that's it, and we are now finished this module, this chapter. Thanks for watching. Have a great day.